Let's go back to the rules and let's do the S equals n minus a rule. Let's figure out the total number of available electrons for this particular structure. We've got sulfur and we've got oxygen, and we have one sulfur and we have 3 oxygens. And sulfur and oxygen, as it turns out, are both in the same group. They both have 6 valence electrons. So the total available here is going to be 6 plus 18, 24 electrons available to work with to place around that molecule. And then the needed, of course, we have sulfur, 1 sulfur, 3 oxygen. They're normal. They both need 8. And so that's 8 plus 24 equals 32 electrons there needed. So the S equals n minus a rule, we're going to predict that 32 minus 24 equals 8. So the number of bonds then we're going to predict is 8 divided by 2, 4 bonds. Okay, so now let's get started. We're predicting that we need 4 bonds. We're going to let the first atom be the central atom, and we're going to draw the skeletal structure, placing each of the oxygens terminally, because remember, oxygens normally don't bind together unless they don't have a choice, or it's something special like a superoxide or peroxide, which we're not going to deal with in this class. So once I've placed them, then you place the electrons on the terminal atoms. And so what do I have here? I've used 6. I have a total of 24. That means I have 18 left to place. And you just start placing them. You know, this is like a puzzle, remember? It's just sometimes you have to do it and redo it and do it until you get it right. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24. And when I do that and I place my 24 electrons, I find that I have satisfied the octet for this oxygen and this oxygen, but not for this sulfur. I only have 6 on the sulfur, and I only have, oh, wait a minute, no, wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, oh, no, I need one more pair here. I have one more pair there. There we go. So sorry. Okay, so I have, oh, there you go. Yeah, 8 plus 8 plus 8 is 24. It's always 24. So anyway, I have satisfied the octet for all of my oxygen, but I have not satisfied my octet for my central atom. I don't have any more. I mean, you can consider this just like a bag of electrons here. These available electrons are just like all of the outer electrons that you just scraped off of all of these individual atoms and placed in the bag, and now you're resorting where the electrons go. And in this case, I have used all of them, and my sulfur is still not satisfied. So according to the rules, you can take, you know, a bonding pair and, a non-bonding pair and form a double bond. And when you do that, and I'm going to get another piece of paper so I can, when you do that for sulfur, for sulfur trioxide, what you end up making then is this double bond here, and then I have 2 electrons. Ooh, sorry. I have 2 electrons there, and then I still have this oxygen with its 6, and this oxygen with its 6. Okay? And again, you know, who's to say that I could have chosen that pair of electrons to make the double bond? I've satisfied the octet. There's 8 around all the oxygens. Now with the double bond, there's 8 around the sulfur. But why didn't I pick the pair of electrons here? Well, I could have. Okay, and so I could have done it this way. Okay, whoops. It's a little tight there. Or I could have done it from the other side. Okay, from this side. So my double bond could have appeared in one of 3 places. And as it turns out, as in the case in the previous example as well, where we have an either-or situation, this is called a resonance structure. And what happens in reality when you check on this particular molecule, and what I need to tell you now is that double bonds are stronger than single bonds. If I want to break this molecule apart, I have to add more energy, either in the form of electrical energy or heat energy or some form of energy, radiant energy, to this molecule. It's going to take more energy to break a double bond than a single bond, and that's called the bond strength. double bonds are stronger than single bonds. Triple bonds are even stronger still than double bonds. So single bonds are the weakest. And what the chemists have found when they take a close look at this type of a structure where the double bond could have been in any one of these three locations is that it really sort of floats around in all three locations. And the bonds, the actual bonding scheme of this molecule, it's resonating, that's why it's called a resonance structure, between those three different locations. Okay, it's a resonance structure. And so this double bond is really kind of flipping around. And when you measure the bond strengths of the three SO bonds, it's not that one SO bond is much stronger than the other two. They're all about the same. And so what that's telling us is that there's some intermediate phase where this pair of electrons is actually being shared among all three. And so it's sort of like a 1 1/3, a 1 1/3, and a 1 1/3 bond instead of a double, single extreme. So the actual structure is actually somewhere in between these three extremes. And sometimes it's even drawn like this. Where there's kind of a dashed line between all three of those bonds, meaning that pair of electrons is sort of cycling its way through the molecule. It's called a resonance structure. Okay, so it's not a full double bond or a full single bond. It's somewhere in between for all three. All right, so that's a special situation there. And it occurs when you can form a double bond and it's not going to change the structure of the molecule. If you put it here or there, it's still the same.